Okay, so now let's put these principles into work by using them to sample directions on a hemisphere. Okay, now it's almost like the disk. Okay, so we have a point, and this point has polar coordinates, or in this case spherical coordinates, r, theta, and phi, and they are related to Cartesian coordinates x, y, z. X, y, z. How? So x is equal to r sin theta. So theta is this angle. Cos phi. Y is equal to r cos theta. Right? R cos theta. And z is equal to r sin theta sin phi. Okay? So just like the polar coordinates, just like the mapping for a disk for polar coordinates, we have the mapping between the spherical coordinates and the xyz coordinates. Okay, now what is the Jacobian of this transformation? Okay, so the Jacobian of this transformation is actually the following. It's this matrix. Again, we will take derivatives with respect to r, theta, and phi. But you will not do it individually here. I recommend you to try it yourself. So the Jacobian is actually sin theta cos phi. Okay, r cos theta cos phi. Okay, and then minus r sin theta minus r sin theta sin phi. This is the first row. The second row is cos theta minus r sin theta, okay, 0, and sin theta sin phi, r cos theta sin phi, and r sin theta cos phi, r sin theta cos phi. Okay, what is this? The first column is actually the first column represents dx over dr. Okay, the first column, this is dx over dr, this is dy over dr, this is dz over dr. Okay, dx over d theta, I think in this case, dy over d theta, dz over d theta, dx over d phi, dy over d phi. Here you can see 0, right? Because there is no phi term here. And then this is dz over d phi. Okay. Now the determinant of the Jacobian gives us the following. It's equal to r square sin theta. Okay, r square sin theta. Now this is how this transformation from the polar to Cartesian kind of like distorts the space, or shrinks or enlarges the space. Okay, so you can see like if we spend a few minutes investigating this determinant, it's related to r squared, proportional to r squared. For the disk, it was proportional to r, right? It makes sense because now this is a volume, and the volume area, the surface area, is growing by r square. Okay, but it's also related to sin theta. Now here we are in ray tracing not generally interested in sampling points inside the ball. Okay, we are interested in sampling points on the sphere. So we are interested in surface points. Okay, so we are not interested in like uniformly sampling the inside of the sphere. So for our case, actually, we can set R to 1. Okay, we can set R to 1. Now, when you set R to 1, you obtain the following relationship. So probability of theta phi is equal to okay, so remember, we divide this by the Jacobian, determinant of the Jacobian, but r is equal to 1, sin theta is equal to probability of x, y, and z. Okay, so I set R to 1. The reason that of setting R to 1 is I'm interested in sampling points on the surface. And this can be thought of as a unit sphere. Okay, I'm sampling points on the surface of a unit sphere. Okay, so then if you rewrite this, so probability of theta phi is equal to sin theta times probability of x, y, and z. Now, I want to sample uniformly, right? I want every direction to have equal probability for me. Okay? Now, in this case, the probability of x, y, z should be c, constant. Okay? So, from here, if I want to sample points uniformly, I must select my theta and phi such that the probability of theta and phi should be c times sin theta. C means constant. Now we will look at how to find C from the normalization requirement. Basically, the integration of this PDF must add up to 1.